Hello dear student. In the last video, we have discussed about processor chips for embedded applications. We had seen that microcontrollers are a type of general purpose processors widely used in many embedded systems. In this video, we will discuss in detail the architecture and working of these microcontrollers in detail. Welcome to the video. In this video, we will see the components of a microcontroller. We will look into the architecture, the working different registers of a microcontroller in their parallel input-output ports, their series input-output ports, their counters or timers, their interrupt control mechanism. As an example, we will look into Intel 8051 microcontroller, its architecture, pin description, interrupts and its applications. A microcontroller is a small computer on a single metal oxide semiconductor integrated circuit chip. It is a single task oriented and consists of functional blocks for its working such as processor, memory, registers, caches, time units, interrupt control units and input-output ports. A microcontroller chip should be versatile enough to serve a wide variety of applications. The figure here shows the block diagram of a typical chip. The main part is a processor core, which may be the basic version of a commercially available microprocessor. Usually, we choose microprocessor architecture that has a proven and to be popular in service. It is useful to include some memory in the chip, sufficient to satisfy the memory requirement of small applications. Some of these memory has to be RAM type to hold the data that change during computations. Some should be read-only type to hold the software because the embedded system usually does not include a magnetic disk. To allow cost-effective use of low-volume applications, it is necessary to have a field programmable type of ROM storage. Popular choices of a realization of this storage is EEPROM and flash memory. Several input-output ports are usually provided for both parallel and series interfaces, which allow easy implementation of standard I/O connections. In many applications, it is necessary to generate control signals at programmable time intervals. This task is achieved easily by a circuit timer included in the chip. Since the timer is a circuit that counts clock pulses, it can also be used for event counting purposes. For example, to count the number of pulses generated by a moving mechanical arm or a rotating shaft. An embedded system may include some analog devices. To deal with such devices, it is necessary to be able to convert the analog signal into digital representation and vice versa. To be conveniently accomplished, we add analog to digital converters or digital to analog converters in the circuit. Many embedded processor chips are available nowadays commercially. Some of the main are Intel's 8085, MCS96 families, CISC style processor cores, the ARM microcontrollers, the RISC type microcontrollers, etc. A simple microcontroller. The input-output structure of a simple microcontroller has to be flexible enough to accommodate the needs of different applications and make good use of pins available in the chip. For example, a parallel port may be configurable as either input or output. In this section, we will discuss the possible organization of the simple microcontroller to illustrate some typical figures. Figure here is a block diagram. This is a processor core on-chip memory. Since the on-chip memory may not be sufficient to support all the potential application of the processor bus, its bus connections can be provided with more pins, and it is connected to external memory, and external memory can be added. There are two 8-bit parallel interfaces which we call as port A and port B. One serial interface. The microcontroller also contains a 32-bit counter or timer which can be used to generate internal interrupts at programmed time intervals to save as system timer and to count the pulses of the input line to generate square wave outputs and many other functions. Let's look into the parallel input-output interface of a simple microcontroller. Embedded system applications require considerable flexibility in input-output interfaces. Consider the example of a microwave oven. It has many I/O interfaces. A sensor is needed to generate a signal with the value 1 when the door of the oven is open. This signal is sent to the microcontroller on one of its pins as an input interface. The same is true for many other keys on the microwave's front panel. Each of these simple devices produces a bit of information. Similarly, for I/O interfaces of fan, light, speaker, LED displays, etc. One of the objectives of the design of input-output interface of a microcontroller is to reduce the need of external circuitry as much as possible. The microcontroller is likely to be connected to simple devices, many of which require one input or no output signal, or sometimes no input or output signal line. In most of the cases, no encoding or decoding is needed. Each parallel port in this figure here is associated with a 8-bit data register, and it is used to configure the individual data lines, either input or output. The figure given in this slide illustrates a bidirectional control of 1 bit of port A. Here the port pin PAI is treated as an input if the data direction flip-flop contains 0. In this case, the activation of the control signal is the read port, and its a logistic value on the port pin points to the data in line DI of the processor bus. The port pin serves as output if the data direction flip-flop is set to 1. The value loaded onto the output data flip-flop under control of the right port signal. It is placed on the pin. Figure shows only the part of the interface that controls the data and data transfer, that is the direction of the data transfer. In the input data path, there are no flip-flops to capture and hold the value of the data signal provided by the device connected to the corresponding pin. A versatile parallel interface may include two possibilities. One where the input data are read directly from the pin, and the other when the input data are stored in a register as an interface. The choice is made by setting a bit in control register of the interface. The figure here depicts all the registers in a parallel interface as well as its addresses at the high end of a 32-bit address range. The status register the PStat, contains the status flags. The PAS in flag is set to 1 when there is new data in port A. It is cleared to 0 when the processor accepts the data by reading it into PA in register. The PAS out flag is set to 1 when the data in the register PA out are accepted by the connected device to indicate that the processor may now load the data into PA out. The interface uses a separate control line to signal the availability of new data in PAS out is cleared to 0. The interface uses new separate control line to signal the availability of new data to the connected device. The PAS out flag is cleared to 0 when the processor writes the data into PA out. The flag used here, PBS in and PBS out, performs the same function for port B. The status register also contains 4 interrupt flags. The interrupt flag such as IA in is set to 1 that the interrupt is enabled and the corresponding IO input action occurs. The input enables the bit are held in control register or PCONT and an enable bit is set to 1 when it is enabling the corresponding interrupt. A single interrupt request signal is used for all ports in the interface. In response to the interrupt request, the processor must examine the interrupt flag to determine the actual source of the request. The information in the status and control registers are used for controlling data transfers to and from devices connected to port A and B. Port A has 2 control lines, CA in and CA out, which can be used to provide an automatic signaling mechanism between the interface and the attached device for devices that have this capability. For an input transfer, the device places new data on port's pin and signifies this action by activating the CA in line for 1 clock cycle. When the interface circuit sees CAN is enabled, that is CAN is set to 1, it sets the status bit PAS in automatically to 1. Later, this bit is cleared to 0 when the processor reads the input data into PA in register. This action also causes the interface to send a pulse to CA out line to inform the device that now the device may send new data to the interface. For an output transfer, the process writes the data into PA out register. The interface responds by clearing the PAS bit to 0 and sending a pulse on the CA out line to inform the device that new data are available. When the device accepts the data, it sends a pulse on the CA in line, which in turn sets the PAS out to 1. This signaling mechanism is operational when all data pins of a port have same orientation, that is, when the port serves as either input or an output port. If some pins are selected as input and others are outputs, then the automatic mechanism is not used and neither the control lines nor the status and control registers contain meaningful information. In this case, the input read directly from pins. Control register bits such as PA register and PB register are used to select the mode of operation of the input ports A and B respectively. If set to 1, a register is used to store the input data. Otherwise, a direct path from the pins is used to indicate that it is in the previous mentioned figure only. Now let's look into the serial input-output interface. A serial input-output interface provides the UART, that is Universal Asynchronous Receiver or Transmitter capability to transfer data. Double buffering is used in both the transmit and receive path as shown in this figure. We have two buffers here. We use a double buffering. And this kind of buffering is needed to handle the burst in input-output transfers correctly. The figure here shows the addressable registers on the serial interface. Input data are read from an 8-bit receive buffer and the output data are loaded to an 8-bit transmit buffer. The status register SStat provides information about the current status of receive and transmit unit. The bit SStat 0, this bit is set to 1 when there is valid data in the receive buffer. This is cleared to 0 automatically upon read access of the receive buffer. The bit SStat 2, this bit is set to 1 if an error occurs during the receive process. For example, an error occurs if the character in the receive buffer is overwritten by a subsequently received character before the character is read by the processor. The status register also contains interrupt flags. The SStat 4 is set to 1 when the receive buffer becomes full and a receiver interrupt is enabled. Similarly, the SStat 5 is set to 1 when the transmit buffer becomes empty and the transmit interrupt is enabled. The serial interface arises an interrupt when either SStat 4 or SStat 5 is equal to 1. It raises an interrupt if SStat 6 is equal to 1, which occurs if SStat 2 is set to 1 and an error condition interrupt is enabled. The controlled register SCONT is used to hold the interrupt enable bits. Setting bits SCONT 6 to 4, these bits as 1 or 0 enables or disables the corresponding interrupts respectively. The register also indicates how the transmit clock is generated. If S count of 0 is set to 0, then the transmit clock is in the same as the system or the processor clocks. If S count of 0 is set to 1, then a low frequency transmit clock is obtained using a clock dividing circuit. The last register in the serial interface is a clock divisor register or a DIV. This 32-bit register is associated with a counter circuits that divide down the system clock signal to generate the serial transmission clock. The counter generates a clock signal whose frequency is equal to the frequency of the system clocks divided by the contents of this register. The value loaded to this register is transferred into the counter. when then counts down is using the system clock. When the count reaches 0, the counter is reloaded using a value in the DIV register. Now let's see the counter or timer of a simple microcontroller. A 32-bit countdown circuit is provided for use of either a counter or a timer. The basic operation of the circuit involves loading a starting value into the counter when decrementing the counter contents using external or internal clock system or an external clock signal. The circuit can be programmed to raise an interrupt when the counter contents reaches 0. The figure here shows the registers, addressable registers with their addresses associated with a counter or a timer circuit. The associated counter register CNTM can be loaded with initial value when the transfer and it is transferred to the counter circuit. The current contents on the counter can be read by accessing the memory addressed by this register, and the control register CT-CON is used to specify the operating mode of the control or the timer circuit. It provides a mechanism for starting and stopping the counting process for enabling interrupts when the counter contents are decremented to 0. The status register CT stats reflect the state of the circuit. There are two modes, the counter mode and the timer mode. The counter mode is selected by setting the bit, the CT control 7th bit, to 0. The starting value is loaded into the counter by writing into the register CNTM. The counting process begins when the bit CT control of 0 is automatically cleared to 0. The counter is decremented by the pulses in the counter line. That is, you see this figure, it is decremented by the counter line on this counter in line. Upon approaching 0, the counter circuit set the status flag in CT stat of 0 to 1 and raises an interrupt if corresponding interrupt enable bit has been set to 1. The next clock pulse causes the counter to reload the starting value, which is held in the register CNTM register, and the counting continues. The counting process is stopped by setting the bit CT control 1 to 1. We can stop the process of counting. In timer mode, the CT control 7 is set to 1. This mode can be used to generate periodic interrupts. It is also suitable for generating a square wave signal on the output, this timer out line. The process starts as explained in the counter mode. As counter counts down, the value of the output line is held constant. Upon reaching 0, the counter is reloaded automatically with the starting value and the output signal on the line is inverted. Thus, the period of the output signal is twice the starting counter value multiplied by the period of the controlling clock pulse. In timer mode, the counter is discriminated by a system clock. Now let's see the interrupt control mechanism in a simple microcontroller. Let's consider a processor that has two interrupt requests, say IRQ and XRQ. The IRQ input is used for interrupt raised by the input-output devices with the microcontroller. The XRQ input is used for interrupt raised by external devices. If IRQ input is asserted and interrupts are enabled, the processor executes an interrupt service routine that uses the polling method to determine the source or the sources of the interrupt request. This is done by examining the flags in the status register such as PStat, SStat and CTStat. The XRQ interrupt have higher priority than the IRQ interrupts. The process status register or the PSR has 2 bits for enabling interrupts. The IRQ interrupts are enabled if the 6th bit of the PSR is set to 1 and XRQ interrupts are enabled if the 7th bit of the PSR is enabled to 1. When the processor accepts an interrupt, it disables further interrupt at the same priority level by clearing the corresponding PSR bit before the interrupt service routine is executed. A vectored interrupt scheme is used with vectors for IRQ and XRQ interrupts in memory locations, that is 0x20 and 0x24 respectively. Each vector contains the address of the first instruction of the corresponding interrupt service routine. This address is automatically loaded into the program counter or PC. The processor has a link register LR which is used for subroutine linkage. A subroutine call instruction causes the updated contents of the program counter which is required to return address to be stored in the LR prior to branching to its first instruction in the subroutine. There is another register IRA which serves as a return address when the interrupt request is accepted. In this case, in addition to saving the return address in IRA, the contents of the process status register or the PSR are saved in the process register IPSR. Return from the subroutine is performed by the return S instruction which transfers the content of LR into PC. Return from an interrupt is performed by return I instruction which transfers the content of IRA and IPSR into PC and PSR respectively. Since there is only one IRA and IPSR register, nested interrupt can be implemented by saving the contents of the register on a stack using the instructions in the interrupt service routine. Note that if the interrupt service routine calls a subroutine, then it must save the contents of the LR because an interrupt may occur when a processor is executing another subroutine. Now let's look into the 8051 microcontroller as a simple example to learn how these things works. 8051 microcontroller is designed by Intel in 1981. It is a 8-bit microcontroller. It is built with 40 pins DIP dual inline package, 4 KB of ROM storage and 128 bytes of RAM storage. There is 2 16-bit timers. It consists of 4 parallel 8-bit ports which are programmable as well as addressable as per the requirement. An on-chip crystal oscillator is integrated in the microcontroller having crystal frequency of 12 MHz. Now let us discuss the architecture of 8051 microcontroller. In the following diagram shown here, the system bus connects all the support devices to the CPU. This system bus consists of an 8-bit data bus, a 16-bit address bus, a bus control signals. All other devices like program memory, ports, data memory, serial interface, interrupt controls, timers and the CPU are interfaced together through the system bus. This is the 8051 pin description. The pins 1 to 8. These pins are known as port 1. This port does not serve any other function. It is internally pulled up bidirectional input-output port. Pin 9 is reset pin, which is used to reset the microcontroller to its initial values. Pin 10 to 17 is port 3. This port serves some functions like interrupts, timer input, control signals, serial communication signals, RxD and TxD, etc. Pins 18 to 19 are used for interfacing with external crystal to get the system clock. Pin 20 provides the power supply to the circuit. Pins 21 to 28 is port B. It serves as the input-output port. Higher order addresses bus signals are also multiplexed using this port. Pin 29 is a PS enable pin, PSEN pin, which stands for program store enable. It is used to read a signal from the external program memory. The EA pin, which stands for external access input. It is pin number 30 is the EA pin. It is used to enable or disable the external memory interfacing. Pin 31 is the ALE pin, which stands for address latch enable. It is used to demultiplex the address data signal of port. The pin 32 to 39 is known as port 0. It serves as an input-output port. Lower order addresses and data bus signals are multiplexed using this port. Pin 40 is again used for the power supply. There are different types of interrupts, particularly 5 interrupt sources for 8051 microcontroller. The TF0, that is timer 0 outflow interrupt, TF1 timer 1 overflow interrupt, int 0 external hardware interrupt, int 1 is also external hardware interrupt, RIOTI is serial communication interrupts. Interrupts are events that temporarily suspend the main program, pass the control to an external source and execute their task. It then passes the control to the main program where it was being held or left off. Each interrupt can be enabled or disabled by setting the bits of IE register, and the whole interrupt system can be disabled by clearing the EA bit of the same register. Now let's see some applications of 8051. The microcontroller 8051 applications include a large number of machines, principally because it is simple to incorporate in the projects or assemble into machines around us. The following are some of the key spots that are in the spotlight. The first is energy management, that is the electric meter you see in your houses. Competent measuring device systems aid calculating energy consumption in domestic and industrialized purpose. These meter systems are prepared competent by integrating microcontrollers. Another one is touch screens. A high degree of microcontroller suppliers integrate touch sensing abilities in their designs. Transportable devices such as media players, gaming device, cell phones are some illustrations of microcontroller integrated with touch screen sensing. It's also used in automobiles. The microcontroller 8051 discovered board recognition in supplying automobile solutions. They are extensively used in hybrid motor vehicles to control the engine variation. Also, words such as a cruise power or anti-brake mechanism have created it more capable with the amalgamation of microcontrollers. Another use is in medical devices. Handy medical gadgets such as glucose or blood pressure monitors being used to play in microcontrollers and to put a view on the measurements as results, offering high dependability in giving correct medical results. So dear students, in this video we have learned about the architecture and working of a microcontroller by looking into an example of Intel 8051. See you in the next video. Thank you.